In this video, we're going to be taking a look at why these four red circles meet at the point M here. Suppose you have a quadrilateral ABCD and the circumcircles of ABF, ADE, EBC, and FDC, and we draw them in red. And we want to prove that they pass through this point M. M lies on all of these circles. How might we get started on proving this really nice theorem? In order to do so, we need to define a new concept called spiral similarity. So what is that? If you have two line segments A, B, and then CD, then a spiral similarity is centered at a point O, suppose. Hold on. O, over here. And it's such that triangle OAB is similar to triangle OCD. In other words, that means that we can rotate AB through O and then finish off with the homotopy, centered at O again. Convince yourself that there's only one spiral center. A spiral center is a point O in this example. Convince yourself that there's only one, and there can't be two, suppose, or that it can't exist. So now that we know there's exactly one spiral center, where is it? Well, it turns out that if we draw the lines AC and BD and they intersect at a point X here, then that means that, and then we draw the circumcircles of ABX and XCD, and the second intersection point is a point O. Then it turns out that O is a spiral center. So how can we prove this? Our goal is to show that triangle OAB is similar to triangle OCD. And the best way to do so is to prove that the corresponding angles are equal. So let's go ahead and start with angle AOB. So directed angle AOB is equal to directed angle AXB, which is also directed angle CXD because AXD are collinear as are BXD. So that's CXD, and that's equal to COD in turn. And now let's go ahead and prove that BAO and DCO are equal. So we have directed angle BAO is equal to directed angle BXO because of the cyclic quadrilaterals. And this is equal to directed angle DXO because BXD are collinear. And this is equal to directed angle DCO. And therefore, since we prove that these triangles are we have these equal angles, we know that these triangles are therefore similar. And they are similarly oriented. But there's more to the story, actually. On top of that, we have triangle AOC is similar to triangle BOD. In other words, O is a spiral center mapping AC to BD. So how can we get started on proving this? Well, it's another simple angle chase. We might want to do CAO and ACO. So directed angle CAO is equal to directed angle XAO, which is directed angle XBO, and this is also directed angle DBO. And as for directed angle ACO, this is equal to directed angle XCO. This is directed angle XCO because of the cyclic quadrilaterals. And XCO is equal to directed angle BDO. So therefore, this also holds. In other words, if AB and CD, if O is a spiral center mapping AB to CD, it's also the spiral center mapping AC to BD. So if you have the line segments AB and CD, A gets mapped to C, B gets mapped to D, then you take the first points in each and the second points in each, and draw the line segments connecting those, so AC and BD. And that means that O is the spiral center mapping AC to BD. And given this, let's go ahead and solve this problem here. We have lots of intersections of circles now, so we immediately think of spiral similarity. Indeed, AD and BC intersect at a point F, and the circumcircles of FAB and FDC intersect at a point M. So that means that we can immediately deduce that M is a spiral center mapping AB to CD. So AB to DC. So triangle MAB is similar to triangle MDC. But because of the duality that we proved, this is equivalent to saying triangle MAD is similar to triangle MBC. In other words, M is a spiral center mapping AD to BC. And now here's a catch. We draw AB and CD and the intersect at a point E, and because M is a spiral center, M must lie on the circumcircle of EDA and EBC. So there you have it. M is a unique spiral center mapping AB to DC because it lies on these two circles, and in turn, it's a spiral similarity mapping BC to AD, which means that it lies on the other two circles. And this point M is called the Miquel point. And the theorem that underlies its existence is called Miquel's theorem. It's a very powerful fact, and the Miquel point is really nice and particular, and I will explore it in a later video. So thank you so much for watching. I hope you enjoyed.